Welcome to our channel. Let's begin the journey.
Let's dive right into this explainer. Today, we're unpacking the geometry of chance, specifically neutron cross-sections. We're going to explore the incredibly colorful, high-speed, microscopic world inside a nuclear reactor core to see the foundational physics that literally make nuclear power possible. And specifically, we're focusing on how pure chance, governed by some truly fascinating quantum geometry, manages to sustain a nuclear chain reaction.
Because, to truly grasp how we generate nuclear energy, which powers massive chunks of our electrical grid today, we have to ask a pretty fundamental question. How exactly do you train a chaotic, lightning-fast particle to do exactly what you want? Inside a reactor core, we aren't building some predictable clockwork machine. We're actually managing a continuous, incredibly high-stakes lottery down at the subatomic level.
Section 1. Born fast, going nowhere. Let's meet the protagonist of our chalkboard journey. A newly born neutron. Imagine this little guy has just been violently ejected from a uranium nucleus that's split apart. It's just entered the world, and man, it is in an extreme hurry. This newborn particle is what physicists call a fast neutron. It's rocketing out of that split nucleus with a kinetic energy of around 2 million electron volts. That's 2 MeV. To put that insane number into perspective, the thermal energy of the atoms in the room temperature water surrounding it is just a tiny fraction of a single electron volt. So our neutron is practically shattering the speed limit of its environment.
But here's the massive catch. Instinctively, you might think a faster, more energetic bullet would be way better at smashing into the next uranium atom to keep the chain reaction going, right? Well, the quantum realm doesn't work like that. At these extreme speeds, the probability of our fast neutron successfully splitting another uranium-235 nucleus is incredibly low. To actually be useful, to sustain that chain reaction, our speedy protagonist needs to become a sluggish, low-energy thermal neutron, dropping its energy all the way down to less than 1 electron volt.
So let's move to Section 2, the geometry of chance. To understand exactly why speed matters so much here, we need to look at the mathematical probabilities that govern this giant quantum pinball machine. It's all about a core concept called cross-sections. If you think of the reactor core as a massive game of chance, we need a way to measure the probability of a neutron interacting with a chunk of target nuclei. We do this using what's called the microscopic cross-section. You can basically think of it as the effective target area that a nucleus presents to an incoming neutron. If that target area is large, the chance of a direct hit is high. If it's small, the neutron is probably just going to fly right past without doing anything.
Now, because these targets are unimaginably small, this cross-sectional probability is measured in a wonderfully quirky unit called a barn. A barn is 10 to the negative 24 square centimeters, literally microscopic. So why on earth is it called a barn? Well, during the early days of nuclear physics, scientists joked that for a tiny neutron, hitting a nucleus with a large cross-section was exactly like trying to hit the broadside of a barn. So the absolutely crucial point here is how the neutron speed affects the size of that target. There's a rule of thumb in nuclear physics, known as the 1v law, where v is velocity. Thanks to the wave-like nature of quantum mechanics, a slower-moving thermal neutron spends way more time near the nucleus and effectively sees a much larger cross-section. By hitting the brakes on the neutron, we are essentially inflating the size of the target barn, drastically boosting its chance to cause that vital fission reaction.
Section 3, bounce or be swallowed. Slowing down is definitely easier said than done. As our fast neutron zips through the reactor trying to find its target, it faces a pretty perilous journey. Let's break down the actual physics of the collisions it might experience. When a neutron meets a nucleus, it generally faces one of two distinct fates. It's either going to undergo a scattering reaction, meaning it bounces off a nucleus and changes direction, or an absorption reaction, where the neutron actually penetrates the nucleus and is completely swallowed up. Let's look at the bouncing options first. In a potential elastic scattering event, the neutron bounces off the nucleus exactly like a billiard ball. It never actually penetrates the nuclear surface. The kinetic energy is perfectly conserved during this interaction. The neutron just deflects into a new direction, transferring a bit of its speed to the nucleus it hit, very much like a cue ball smacking into an 8-ball. Then we have inelastic scattering, and this one is a bit wilder. Here, our neutron is briefly absorbed by the target nucleus, but then it's quickly re-emitted.
The catch is, it leaves with less energy than it started with. It transfers so much energy during the hit that it actually leaves the target nucleus in an excited state. Eventually, that excited nucleus has to calm back down, and it usually does so by firing off a gamma ray. So kinetic energy is not conserved here, and the neutron loses a massive chunk of its momentum. All right, now for the swallowed scenarios. The absolute most common pitfall for our neutron is radiative capture. This is a total dead end. The neutron gets swallowed for good. The target nucleus absorbs the binding energy of the neutron, gets highly excited, and de-excites by emitting a gamma ray. This absorption might even cause the nucleus to transform into a highly radioactive heavy isotope, an incredible Hulk of the microscopic world. If this happens, we've lost our neutron entirely, and it definitely won't be causing any fission.
But if we avoid that dead end and our neutron is absorbed by the right heavy nucleus, say uranium-235, while moving at that perfect, sluggish thermal speed, we hit the jackpot. It causes our ultimate goal, fission. The heavy nucleus becomes incredibly unstable, splits right in two, releases a massive amount of heat, and ejects 2 or 3 brand new fast neutrons to start the whole cycle over again.
Section 4, the moderator's crucial role. Let's tie this all back to the actual engineering of a reactor. We've got a fast neutron that needs to become slow, but if it hits the wrong things on the way down, it turns a nucleus into the Incredible Hulk and we lose it. So how do we physically engineer the reactor environment to safely hit the brakes? Enter the moderator. The moderator is this crucial mentor material placed directly inside the reactor core. Its one and only job is to safely guide our fast-moving protagonist down to those perfect thermal speeds without absorbing it. It's basically the ultimate cosmic brake pad. And the choice of that moderator material is absolutely critical. Think about it. A neutron bouncing off a heavy nucleus is like throwing a ping pong ball at a bowling ball. It just bounces off with almost the exact same speed it started with. But if it undergoes elastic scattering on a very light nucleus, like hydrogen, which is roughly the same mass as the neutron itself, it transfers a huge amount of its kinetic energy in a single collision. It's like a billiard ball dead centering another identically sized billiard ball. It can stop almost completely. And this is exactly why nuclear reactors use materials packed with light elements. Ordinary water is fantastic because it's full of lightweight hydrogen. Heavy water uses deuterium, which has an incredibly low microscopic cross-section for absorption, meaning it almost never swallows the neutron. Graphite, which is pure carbon, is another excellent, cheap, and highly effective moderator. They all step down the neutron's energy swiftly, and most importantly, safely. By packing the core with this specific moderator, we complete what physicists call the neutron cycle. We safely guide the neutron from a chaotic 2 million electron volt birth through a perilous maze of potential scattering and absorption events, all the way down to a sluggish thermal state. This perfectly calibrated cycle is what successfully sustains the controlled chain reaction that heats the coolant, spins the turbines, and literally powers our modern world. When you step back and realize that the massive electricity grids powering our homes, our hospitals, our entire cities rely entirely on these perfectly moderated, microscopic rolls of the dice, it's honestly awe-inspiring. It leaves you wondering, as we desperately look for reliable, carbon-free baseload power, just how far we can push this perfect geometry of chance in the next generation of reactor designs. Thanks for joining me on this explainer, and keep questioning the mechanics of the world around you.
The view from here is breathtaking. Command, we are in position and ready for the next phase. If you liked the video, subscribe and comment the topic you want next. Thanks for watching, and stay unstoppable.